So we've solved equations like this before. It's not anything terribly difficult. If we have a fraction, what we do is we clear that fraction. So the way we talked about that before is we use what some classes will call fraction busters. Basically, that just means multiply by, or at least common denominator, multiply those sides by 2x plus 1. I can do that as long as what I do to one side, I do to the other. On the left side, that clears the fraction for us, leaving us with just x plus 2 is equal to 2x plus 1. Technically, I distributed that 1 in there, didn't make a difference, but we multiplied it in. And then we could just solve this. Isolate the variable on one side, subtract that away, and x equals 1. Not too hard. Another way I could have solved this is actually by analyzing it by graphing. So I could have taken that x plus 2 over 2x plus 1, and I could have taken that 1, and I could call this f of x, and this g of x. So I could graph x plus 2 over 2x plus 1. Okay, and I could graph 1. And I can find out where do these cross. Look for the intersection here. They cross at 1, 1. They cross when x equals 1. So this one was kind of like this. That was our f of x. G of x would have been just the horizontal line at 1. And they cross right here at x equals 1. That works, but actually what I would encourage you to do is rather than set f of x equal to g of x, I would rather that we do f of x minus g of x and set that equal to 0. What do I mean by that? Well, take the, x plus 2 over 2x plus 1 set equal to 1, and just get it set equal to 0. Minus 1 there. So what you really end up with is x plus 2 over 2x plus 1, all minus 1, and then I can find out where does that equal 0. And I know that seems more complicated, but just stick with me. There will be a point to this. So real quick, first thing we're going to do is we're going to clear out this. And then the other one, all I need to do is add a minus 1 here. What does that do for me? Well, now I'm trying to find out where does this equation equal 0. So where is it on the x-axis? Well, if I check this, analyze 0, there's my 0. It crosses at, at 1. So what does that do for us, right? Well, it makes the next question a lot easier because that was just solving where it equals 1, with x equals 1 right there. What if I said, where does where is that greater than 0? I'm sorry, it wasn't a 0. Greater than, what was it, 1 initially? So rather than look at this, I would rather look at that x plus 2 over 2x plus 1 minus 1. Where is that greater than 0? I'm treating this as our function up here, right? So where is it greater than 0? Well, everything right here to the left of that solution, right? But it doesn't go further because down here it's less than 0. So it doesn't stay forever. If I just solved this, you would end up getting x is less than 1, which is actually a lie because all down here, that's not part of our solution, is it? So this is where the algebra actually ends up being wrong. And we have to use the graph to help us understand this solution works starting at 1 and to the left, but it stops right here. Where does it stop? Well, this point where it stops is called the vertical asymptote. So we have to find the vertical asymptote to this graph, which is not hard. The vertical asymptote's easy. We take the denominator and say, what makes it 0? Minus 1, 2x equals negative 1. So how about negative 1/2? And what does that do for me now? Well, where is this graph above 0? Well, negative 1 to the left, but it never reaches that negative 1/2. It stops. So really the answer to this question right here is from our asymptote, negative 1/2, to the 1. This is the interval from the vertical asymptote to negative 1. That's the only region it's above 0. I can make it even, a little crazier. X plus 2 over 2x plus 1 less than or equal to 1. Where does that happen, right? If I solve this, I would only get x is greater than or equal to 1. That's true. That region right there, change the highlighting here. That region right there, that is less than or equal to. But all of this answer got completely ignored, and all of that answer actually works. So where is that answer? Well, from negative infinity to our asymptote. So where is it less than? Between negative infinity to our asymptote, or starting at 1 to infinity. So this actually has two answers to it. Only one you can get algebraically. The other one you have to get by visualizing it, by graphing it. So I recommend that you get the equation set equal to 0, and then see where the graph's above 0, below 0, and you need to find the asymptotes. Let's practice some more of this. I know that's probably was a bit overwhelming for our first example. So again, if I were going to solve this algebraically, we would have done this in an intermediate algebra. All we would have done is find out the least common denominator. And the way we would do that is by going, okay, this one has an x minus 2. This one has an x plus 2. And the last one, it needs to be factored. X squared minus 4 actually factors to x minus 2, x plus 2. So that is really our least common denominator. And then what I do is I multiply each group by x minus 2, x plus 2, x minus 2, x plus 2, x minus 2, x plus 2. On our first one, the x minus 2's cancel. Second one, the x plus 2's cancel. And on the last one, the whole group with the whole group. Now distributing, we get x squared plus 2x, and we get plus x minus 2, distributed to 1, equal to, and now just 8. combining like terms, and since this is looking quadratic, I'm going to set this equal to 0 while I'm at it. So we get x squared plus 3x minus 10 equals 0. I think we can solve that. How about x and x? 5 and 2. Positive 5, negative 2. So x equals negative 5 and x equals 2. I think we can check that graphically. Now, rather than call this all f of x and this all g of x and setting them equal to each other, again, if I'm going to check this graphically, then what I really want is this set equal to 0. So I'm going to actually subtract that group over so that I end up with x over x minus 2, 1 over x plus 2, minus 8 over x squared minus 4. And I'm going to graph all of this mess and find out where it equals 0. So we said x over x minus 2 plus 1 over x minus 2 There we go. And then it was minus 8 over, and it was x squared minus 4. I'm sure that's all right. Okay. So we said we thought this was cross at negative 5 and 2. Something's wrong. Weird. See, like this is doing some really strange things because I'm looking at this going, well, analyze this graph. I see the 0 we wanted, but that's not there. So, oh, that first one, there's my problem. That first one, geez, I thought I checked that. Was supposed to be, was that supposed to be x plus 2? No, second one's supposed to be x plus 2. Okay, knew something was off there. Hopefully yours is not this complicated to use. There we go. Minus 2 plus 2. All right, that's more what I was looking for. Okay, so look, it crossed right there at negative 5, 0. Did not cross again at 2, did it? It got that solution. When I graphed this, I see this crossing at 1, 2, 3, 4, 5. Right? Go back to my graph here. All right. And then, oops, calculator go. But it never crosses again. So that means that that answer right there is not a right answer. In the past, we've called those extraneous solutions. They're answers that we get algebraically, but when we check them, they don't work. In fact, if I had plugged in both of those numbers into the algebraic equation, that too would not have been correct. So you need to check these graphically. Basically, this graph has a hole where? At the domain. So it has a hole at -2 and at +2. So this graph does not exist there. So there's basically a hole right here. And that's where we don't have a solution. So I move on to our third example. If I was going to solve this algebraically, right, our common denominator, neither of these really have anything in common. This one and this one. So our least common denominator would have to be an x and an x minus 2. So this first one we'd have to multiply by x and x minus 2. Second one by x, x minus 2. Third one by x and x minus 2. Here these x's would cancel, leaving us with just x minus 2. Here the x minus 2 would cancel, leaving us with minus x. And here everything would remain, leaving us with really 2x times x minus 2, or 2x squared minus 4x. This is looking pretty quadratic. I'm going to clean it up though. These cancel out, leaving me with just -2. So I would add the 2, getting this set equal to 0. And then let's see if this factors. I do see all of these have a factor of 2. And then what's left, I think factors x times x minus 1 minus 1. And we get x equals 1. So what would I graph if I wanted to see this, right? I would not graph these two equations. What I would do is take the equation and I would get it set equal to 0. So really 1 over x minus 1 over x minus 2, all minus 2 equals 0. And this is what I would graph and find out where does it equal 0. Should be at 1. Okay? One over x minus, if I'm doing this right, 1 over x. One over x minus 2. And then we have minus 2 at the end. Well, there's our solution right there at 1, right? So we know it crosses there at 1, and then it does that weird loop up thing, and then it does this. Well, how would I solve that same equation if I wanted less than 2? Remember, I wouldn't treat it like this. I would get it all on one side and find out where is it less than, so minus 2 there, where is it less than 0? So that would just be this region right here. But what I need is to figure out what are these vertical asymptotes. They're not hard. You get those from the denominator. First one, x cannot be 0. Second one, x minus 2 cannot be 0. So x cannot be 0 is 1, and x cannot be 2 is the other. So really, where is it below 0? From -infinity up to that first 0, or we can back up at 2 to infinity. And again, using this graph one more time, I can do the same thing with 1 over x. Where is it greater than or equal to 2? Well, I would set it all equal to 0. And where is it greater than 0? Everywhere in the middle, between the two asymptotes. So between what? Between 0 and 2. Why am I not using brackets, even though there's an equal to here? Because the dotted line, it never equals 0, never equals 2. Those are asymptotes. So it's between those two numbers. Okay? On this last example, they've done this weird thing by writing all of these with negative exponents. All we're going to do on that is we're going to rewrite these. So we're going to treat this as 7 over x to the 4th minus 8 over x squared plus 1. And then we want to clear out those fractions just the same way we did before. So our least common denominator would be the highest power of x, or x to the 4th. So everything's going to get multiplied by x to the 4th. So we have f of x is equal to 7 minus 8. Those clear out x squared. And this becomes just plus x to the 4th. Now I'm going to go ahead and reorder this. Just in descending order, because we rearranged the exponents, and we actually solved these in our last chapter. This is quadratic by nature because we can have an x squared and x squared, factors of 7 that make 8, and we'd be looking at what, both negative to make a negative 8. And then we can solve this. Our first one says, where is it equal to 0? Well, take each group, set it equal to 0. Our first one, x squared equals 7. Square root that. We get plus or minus root 7. Second one, x squared equals 1. Square root that. We get plus or minus 1. So we have 4 solutions. So in this graph, this should cross the 0 4 times. Okay? So when I do this, it should cross at 1 and negative 1, and root 7, which is between 2 and 3. Between 2 and 3, it should cross as well. So that's positive root 7, and that one is negative root 7. Okay? So let's go ahead and look at this in the calculator real quick. 7x to the negative 4th. So 7x, and if you want to make that a negative, I can raise it to the negative 4th, or you could rewrite it as the fraction like we did. And then what was it? Minus 8x to the negative 2. So raised to that, negative 2. And then it was plus 1. And this crosses, dang, at 1, 2, 3, 4 times. It's a really strange looking graph, right? Since we have all those x's in the denominator, we do have an asymptote. Basically, we have a vertical asymptote right here. And then the graph comes in and then back up. And right here it does the same thing, where it comes in and then back up. And those are supposed to be symmetric, so I'm going to clean that up a little bit. What that does is it makes these last two a lot easier to answer. Where is it greater than or equal to 0? Well, anywhere it's above. Right? Where is it less than 0? Anywhere below. I'll do the less than first because that's a little easier. Where is it below? Well, here, between negative root 7 and -1, both with brackets, or from here, from 1 to positive root 7, both with brackets. Okay? Where is it greater? Right here, from -infinity to that negative root 7. Infinity in parentheses, root 7 in brackets. Or from -1, and then there's an asymptote, so it actually stops at 0. Bracket there, parenthesis. Or from 0 to +1, or from root 7 to infinity. So there are 1, 2, 3, 4 different regions where it's greater than or equal to 0. This would be a mess to solve algebraically. This is where the graph really helps us get to these answers way faster. 4 solutions, this gives us 4 regions where it's above 0, okay? So that's it for this section. It's a bit hefty on the topics, but I'll be working through the homework, and hopefully that helps you guys get through these and prepare for the upcoming tests. So keep up the hard work.